The interesting thing about arrows is that you can operate with it. You can say, well, I want this system of 3 arrows to be a whole system, and I write it in a more compound way that will catch the whole system. And I write it as an arrow of arrows. You just take those 3 arrows and you add them, and then you have a vector of vectors. That's just another vector. So we have the real particles, the fundamental particles, electrons, and we have compound systems that we describe by an addition of arrows.
Can we say that there is one arrow that is the resultant of the existence of these 3 particles in the system? I mean,
yeah,
the fact that there are these 3 particles
we can say that mathematically we can talk about the resultant arrow.
Because you will come to that the particles are in the space, and does this mean that the fact that these particles are in the space and not very far one from another would result in something that we will represent by this bigger arrow? Or maybe I talk too quickly.
Well, I've put them in one nearer just for convenience.
Okay.
And quantum physicists, they don't think about those little arrows anymore. They take this system, and then they operate on it. But you can also think of it as a compound system of little arrows.
Because the question, I think, was like whether they interact. Whether your needle here interacts such that you can somehow replace these 3 interacting needles by one abstract needle with the resulting properties.
Yes, you always have an abstract needle that will represent the interacting or
so
non-interacting.
they are interacting.
They are interacting or they are not interacting. It depends on the location. It depends on their location. Depends on their energy if they are interfering. But
if they were not interacting, would you put them into that notation together?
Yeah. Quantum physicists put them in one notation. They will say 2 particles that are far apart. They are one quantum system, and we describe it with 1 arrow.
Okay, so in 1 arrow is this big bracket is the whole system of your interest.
Yeah.
Okay.
Yeah. But then it becomes a little abstract then, and then it's difficult to visualize it. But in fact, it are different arrows at different places. Fundamental arrows at different places. So that was the first principle. The second principle is that arrows have a spinning motion. An arrow, you can throw it or with an arc, but often if it's freely in space, it's spinning. And if it's spinning,
in fact, the spinning is the most probable behavior of a needle.
Yeah.
Because of the stability, because of this prevalent dominant symmetry, which is one-dimensional. So whenever it's in motion, subject to a slightest perturbation, it will show the spinning motion.
Yeah, they will always.
Which is the most stable in the.
And also, if you want to interact with this arrow, if it's piercing through the space, it won't interact with much matter around it. But if it's rotating in some way, it will catch up with the other arrows, and so it will have a much more impact, cross-section, we say. So the orientation of the arrow changes, and well, then it becomes a little mathematical, or physicists, they describe rotations with complex numbers. So we have our first arrow, our arrow at a time, at one time, and if it's rotated about an angle alpha, the resultant arrow, it's the same arrow, the same, but after a certain time, they describe it with the same arrow. So this is vector A or arrow A times complex vector that's exponential I alpha, where alpha is the angle. Okay, exponential. Well, so just to give an idea of how physicists explain the rotation of arrows, they draw that arrow. They say after a time, little time, infinitesimal time, dt. After that, it has rotated over an angle omega dt, or delta t, a very tiny time. Yeah, dt. And then they look at the difference between the two arrows. When you subtract an arrow from another arrow, you get a tiny arrow, if it's rotated, which will be directed in this way, and which will be perpendicular, orthogonal to the initial arrow. So they say that this dt times this arrow, difference arrow, d psi, it's psi t plus delta t minus psi t, so the difference. Let me write it differently. T plus delta t minus psi from t,
which is the little arrow difference, right?
Which is this little arrow. It's equal to omega dt times the initial arrow times this arrow, and rotated over an angle 90 degrees. So EI 90 degrees, that's pi divided by 2 for physicists. So this is just a vector, complex vector I. So I have d psi divided by dt, that's equal to I omega psi. I just multiply by a factor h bar at both sides, and I have an equation. I put this on the other side. I reverse time axis, and this is in fact a Schrödinger equation. Maybe this will be a bit difficult to explain, to understand if you've not done some complex numbers or differentials. But this is the form, the general form of a Schrödinger equation, time-dependent Schrödinger equation. Okay. Here I had an h bar omega, but I could say this is the energy. So this is the energy of my arrow or my system of arrows, and I see that the energy times the arrow it's the imaginary I times the differential of my arrow. So that there's for the energy, in fact it's the rate of change of my spinning arrow. So that's Schrödinger equation. Well, we go to the next principle. Observing arrows means interacting with them. You cannot observe a particle, quantum particle, if you don't interact with it. You must have some interaction with them. Okay? Interaction means operating on the arrow. So in quantum mechanics, quantum physicists talk about operators. They have an operation arrow, and when you operate on the arrows,